Yeah, in this section of the dimension analysis, we want to look at few examples that um, are common, that at least every physician, right, every student doing this particular topic know. These are examples that we use in the subsequent sessions because they'll be very useful. At least we need to know them because there will be more complex equation that we'll be looking at, and knowing the dimension analysis of these basic examples will help us to break down the rest. Okay, so let's start with these basic examples, and note that these basic examples, after we are done with them, you should be able to know them by heart of head, right? Because we use them in breaking down very complex equations going forward. So the very first example of dimensional quantity that we have to analyze is the area. So um, area is what? So we say someone say length times breadth or width, right? So, or you can say width. Okay, now let's try to find the dimension analysis of this. So if you are doing the dimension analysis, what do we say? The dimension analysis of area. We bring the square bracket. Whenever you are bringing the square bracket, it means that you are doing dimension analysis. It's going to be equal to the dimensional analysis of length times the dimensional value of breadth as well. Now, if you do that, length is a basic quantity. So when we did the dimension analysis of that, what did we have? We said that dimension of anything that is separation or distance or length or breadth is what? Capital L. Breadth is also like separation, it's also L. So at the end of the day, we have L squared. So the dimension analysis of anything that is area is L squared. So this is the dimensional analysis of this particular um area. So it's L squared. So that's one basic thing that we need to actually know. Let's look at another example. Volume. Dimension analysis of volume. So we know volume is length times breadth times height. Okay. So the same thing, if you are bringing the square bracket, it means that you are now coming to evaluate the dimension analysis of this. It's going to be equal to the dimension analysis of length times the dimension analysis of breadth times dimensional analysis of height. So length is capital L, right? Times breadth is also capital L, and height is also capital L because they are all separations, and all separations are like length. So the dimension analysis of volume is equal to this. Then L times L indices is L cube. So volume is going to be this. Yes. Yeah. That's about volume, right? So we know dimension analysis of area, which is L squared, dimension analysis of volume, which is L cube. The next one is dimensional analysis of density. That's the next one. So we have density, and we know density is equal to mass over volume. Mass over volume. So you do that, you bring the square bracket. So once you are bringing the square bracket, it means that you are coming to start to do the dimension analysis of that. So for each quantity inside, dimension analysis of mass divided by the dimensional value of volume, the dimension of volume. So if you do that, dimension of mass, when we did the previous session, right, is capital M. We did that in the previous session. That mass is capital M, and volume we just did that, and volume is L cube. L cube, right? So but then if you're using indices, the length should go up, it become L to the power negative 3 because it was 3 at the bottom. So if you are bringing it up, then in order to get rid of the division line, you have ml cube. So yes, so the dimension of density, the dimension of density is capital M, capital L to the power negative 3. So only the L is to the power negative 3. This is the dimensional value of density. Great, great, great. Now let's move away from these densities, and then next one we are going to look at velocity. Velocity. What is velocity? Velocity is displacement over time, right? So you have displacement over time, time of change, right? So now if you are doing the dimensional analysis, remember to bring the square bracket so that when we are reading your work, we know that you are finding the dimension analysis. The square bracket. So it's going to be the top. The top is going to be displacement over the dimensional value of time. When we did that, displacement is the same as what? Distance, the same as separation. And anything separation is what? Capital L. And time is what? Capital T from the previous session. So again, we want to bring the T up. So it become L T to the power. Here it was power 1. So it become power negative 1. So the dimensional value of velocity is equal to Lt to the power negative 1. This is the dimensional value of our velocity. So the same thing for speed. If it were speed, it's going to be distance over time, and distance is the same as separation, right? So you obviously get the same thing. That's the only difference between velocity and displacement. So the next thing we look at is acceleration. Acceleration. So what's acceleration? So acceleration is equal to uh, velocity over time. So if it is velocity, right? So if you bring the dimension analysis of velocity, that's acceleration, right? So remember to always bring the square bracket. So the top is going to be velocity, and the bottom is going to be time as well. So now velocity, we just found it for velocity. The dimension analysis of velocity is what? Lt to the power negative 1, right? Over the time is capital T. So if you are bringing that, the one at the bottom, right, is also coming up negative 1. So this one is from the bottom. This is the one that we already have here. So this one is coming from the bottom. So at the top, we have Lt to the power negative 2. So our acceleration is equal to Lt to the power negative 2. Remember, the acceleration is power negative 2 because it's indices. You are just following the laws of indices. When two indices of the same base are multiplying, right, we add the powers. So the powers are negative 1, negative 1. So the two of them become negative 2. Only the t, right? L is not having any particular component. So this is what we have for acceleration. Now let's look at the next one. Now that was acceleration, right? Now let's look at force. Force. The next example is force. Force is mass times acceleration. Acceleration. Yeah. So this is the basic definition of a force in terms of equation. So now the dimension of force. Let's try to find that. So we know that it's going to be equal to dimension of mass times the dimension of acceleration. Acceleration. So now if you do that, for mass is capital M, right? And acceleration, what did we have? We had Lt to the power negative 2 right now. So it's the same thing. So if we bring all of them together, you have mLt to the power negative 2. So this is the dimension of force. This is what we have currently. This is for force. Now the next one, let's try to find it for work, because we now have force, right? So now the dimension of work or energy. So work is a form of energy, right? So all energies, anything that is energy, right, will have this particular unit. But we know that work is equal to force times displacement. Force times displacement, basically. So if you do that, the dimension of work, if you don't bring the square bracket, we will not know what we are doing. So it's needed for us to know that, okay, what we are coming to do is the dimension component of the particular quantity. You see that as we are moving forward, we are making it more complex, right? We are building up on what we knew. So displacement. And then for dimension of force that we found right now, it was mlt to the power negative 2, right? And displacement is what? L. Everything displacement or separation is L. So if you do that, the L and L are there, so right? This is power 1, this is also power 1. So if you put them together in the multiplication, following the law of indices, right? We have ml squared times this. So ml squared is to the power negative 2. This is for work, the dimension of work. Yeah, this is the same for anything that is concerned with energy, right? Yeah. So these are the various basic examples. You can try for momentum, you can try for other quantities as well. But then these are the basic quantities that at least you should know. At least you should know, so that we can use them for. You see that when we're solving some, like before you do the density, we did our volume, and that volume we just use it in the density analysis. When we find acceleration, we use it in the force, and then for force, once we know force, when we are doing work, we're able to use the knowledge that we know from force, right, in order to do the work. That's how the dimension analysis. But these are the basic ones. These are the common ones, at least, that everyone should know. So if you're talking about acceleration, is lt to the power negative 2. If it is displacement, is L. If it's velocity, lt to the power negative 1. If it is anything that's related to work or energy, is this particular one that we have currently, ml squared to the power negative 2. Yes. So in the next session, we'll see the importance of dimension analysis, and then we begin to break them down and solve questions under each importance. See you in the next session.